Thermodynamics, an engineering approach, 9th edition SI units, Cengel, Boles, Kanoglu. Alright, what do we got going on in here? Chapter 1, Introduction and Basic Bitch Concepts. Thermodynamics and energy, application areas, importance of dimensions and units. Man, fuck them units. Some SI and English units. They shit talk English units in this book. It's pretty great. Dimensional homogeneity, unit conversion ratios, system and control volumes, properties of a system, continuum, density and specific gravity, state and equilibrium, the state postulate, processes and cycles, the steady state of process, temperature and the 0th law of thermodynamics, something to do with temperature scales, the International Temperature Scale, ITS 90 of 1990, pressure, under pressure, variation of pressure with depth, pressure measurement devices, the barometer, the manometer, other pressure measurement devices, problem solving, a technique. Step 1, write down a problem, a statement. A step 2, schematic. A step 3, assumptions and approximations. Step 4, physical laws. Step 5, properties. Step 6, calculations. Step 7, reasoning, verification, and discussion. Then we talk about engineering software, equation solvers, a remark on significant digits, the summary, references, suggested readings, homework problems. Then we get into chapter. Okay, great. Background, objectives, philosophy, yada yada doo, self-instructing, extensive use of artwork, emphasis on physics. Oh my gosh, what's new in this edition? Because the special Indian edition. Ha. 9th. The 8 editions 1 through 8 weren't good enough. Or they were just trying to make it big. Energy balance, entropy balance, exergy balance. The physically meaningful forms of the balance equations rather than formulas are used to foster deeper understanding and to avoid a cookbook approach. Fuck the cookbook. I'm making my own recipe. The mass, energy, entropy, and exergy balances for any system undergoing any process are expressed as mass in minus mass out equals mass change. Same. Topics of a special interest. They talk about refrigerators, money, and driving sensibly and saving fuel. Who the fuck highlighted all this shit? Alright, what are we taking away from chapter 1? Identify unique vocabulary associated with thermodynamics through the precise definition of basic concepts to form a sound foundation for the development of the principles of thermodynamics. Review the metric system and the metric SI. Review the metric SI and English unit system. Explain the basic concepts of thermodynamics such as system, state postulate, equilibrium, process, and cycle. Discuss properties of a system and define density, specific gravity, and specific weight. Review concepts of temperature scales, pressure, and absolute gauge pressure. Gauge or gauge? Gag. Absolute gag pressure. Okay. Introduce an intuitive, systematic problem-solving technique. Alright, what do we got? We got the conservation of energy principle. Energy in is equal to energy out. See rock? Rock starts with 10 units PE, potential energy. No units of KE, kinetic energy. Rock falls. Rock lobster. Potential energy goes to 7 units, kinetic energy goes to 3 units. So we're trading. We ain't gambling, we're out here trading. That's a bad analogy. Energy cannot be created or destroyed, it can only change forms. Just as when you eat, energy in, when that is greater than energy out, I had to use the fucking sumo wrestler. You get fat. Same conservation of energy principle, but it's for the human body. The first law of thermodynamics is simply an expression that the conservation of energy principle asserts that energy is a thermodynamic property. So energy transfers. That's what I gather from that. Second law of thermodynamics asserts that energy has quality as well as quantity, and actual processes occur in the direction of decreasing quality of energy. So that is well depicted by this picture where the quality of energy is lower outside of the coffee, therefore it's transferred from the cup to the surroundings. I don't really understand this quality of energy. It makes more sense to me to describe it as energy transfers from a high energy source to a low energy source. At least, I don't know if that's right either. High temperature of the coffee is degraded, transformed into a less useful form, lower quality, at a lower temperature. Alright. Once it is transferred to the surrounding air. So, quality, yeah. Basically, thermodynamics is all about heat power, as they say in the Greek terms. Therm, heat, dynamics, power, which is the most descriptive of early efforts to convert heat into power. The science of energy. We're gonna be all over the place. But yeah. It was the term, first little history lesson. Who doesn't love history? Although the principles of thermodynamics have been in existence since the creation of the universe, thermodynamics did not emerge as a science until the construction of the first successful atmospheric steam engines in England by Thomas Savery in 1697 and Thomas Newcomen in 1712. These engines were very slow and inefficient, but they opened the way for the development of new science. The first and second laws of thermodynamics emerged simultaneously in the 1850s, primarily out of the works of William Rankine, Rudolf Clausius, and Lord Kelvin. God, what a trio. Thermodynamics was used in a publication by Lord Kelvin in 1849. That's only, we're 26 years away from being 200 years ahead of this dude. So we're 174 years older than this publication, which is not a long time, which is incredible. The first thermodynamic textbook was written in 1859 by William Rankine, professor at Glasgow. And then they also talk about classical thermodynamics And statistical thermodynamics, classical is generalization, like it provides a direct and easy way to solve engineering problems. Statistical thermodynamics is more elaborate and based on the average behavior of large groups of individual particles. It's a microscopic approach, rather involved, and it's only used in this text as a supporting role. So basically they're telling you, we're learning about classic thermodynamics, although statistical thermodynamics is definitely more pedantic. We got applications, your body, a house, that's about it. Then we get into dimensions and units. Any physical quantity can be characterized by dimensions. I want to highlight that shit. The magnitudes assigned to those dimensions are called units. Some basic dimensions such as mass, length, time, and temperature are selected as primary or fundamental dimensions. Others such as velocity, energy, and volume are expressed in terms of primary dimensions. They are called secondary dimensions or derived dimensions. A number of unit systems have been developed over the years, despite strong efforts in scientific and engineering community to unify the world with a single unit system. Two sets of units are commonly used today: the English system, United States customary, and the metric SI. Le système from Le Système International des Unités. I want to point out where it says that they're talking shit about how engineers have to remember more units than we actually need to because there are two commonly used systems of units. The recent move toward the metric system in the United States seemed to have started in 1968, another history lesson, when Congress, in response to what is happening in the rest of the world, passed a Metric Study Act. Congress continued to promote voluntary switch to the metric system by passing the Metric Conversion Act of 1975. A trade bill passed by Congress in 1988 set a September 1992 deadline for all federal agencies to convert to the metric system. However, the deadlines were relaxed later with no clear plans in the future. Industries that are heavily involved in international trade, such as automotive, soft drink, and liquor industries, have been quick to convert to the metric system for economic reasons. Having a single worldwide design, fewer sizes, smaller inventories, etc. More efficient. Today, nearly all cars in the United States are manufactured in metric units. Most car owners probably do not realize this until they try an English socket wrench on a metric bolt. Yeah, buddy. Most industries, however, resisted the change, thus slowing down the conversion process. At present, the United States is a dual-system society and will stay that way until the transition to the metric system is completed. This puts an extra burden on today's engineering students, since they are expected to retain their understanding of the English system while learning, thinking, and working in terms of SI. Well, like, he also, yeah, this stuff is good too. The SI is a simple and logical system based on a decimal relationship between various units, and it is being for scientific and engineering work in most of the industrialized nations, including England. The English system, however, has no apparent systemic numerical base, and various units in the system are related to each other rather arbitrarily. There's 12 inches in a foot. 1 mile has 5,280 feet. 4 quarts to 1 gallon, which makes it confusing and difficult to learn. Good shit. But hey, that's why American engineers are the best, because we work in all units. As pointed out, SI is based on a decimal relationship between units. And here we got a nice table of the prefixes. Table 1, 2, standard prefixes in SI units. Now this one gets into, like, this is the most I've seen. I've never seen yada and yocto. We got pico, we got nano. Yeah, past pico, we got femto, atto, zepto, yocto, and beta, exa, zeta, yada, tera, giga, tera. Yeah, buddy. Oh, buddy. Alright, alright. Then we got formulas 1.1. Force equals mass times acceleration. What a good one. That's a good one. Newton's second law. A force is a Newton in SI units. Force required to accelerate one mass, or a mass of 1 kilogram at a rate of 1 meter per second. That's pretty interesting. A Newton defined as the force required to accelerate. In the English system, the force unit, pound force, is defined as the force required to accelerate a mass of 1 slug, 32 at a rate of 1 feet per second squared. Yeah, buddy. Like, dumb. But hey, who cares? And we're 20 minutes in. So this is where you walk away, fill up your cup of water, take a sip of coffee, look at the laser cutter. Alright, let's keep moving. We got formula number 2. Weight is equal to mass times gravity. So a Newton is equal to mass times gravity. And they talk about the conversions, like 4 apples is approximately 1 slug. No, take that back. 4 times 32, so about 120 plus 8, about 129 apples is equal to 1 slug, which is equal to about 32.17 pound mass. Yeah, like, who cares? Stupid. Relative no, it matters. Weight is often incorrectly used to express mass, whereas weight is a force, like a newton or a pound. Yeah. Particularly by Weight Watchers. Unlike mass, weight is a force. Where mass is the body, g is the local gravitational acceleration. So, local on Earth, it's 9.8 meters per second at sea level, and a 45-degree latitude. An ordinary bathroom scale measures the gravitational force acting on a body. The mass of a body remains the same regardless of its location in the universe. Its weight will change based on gravitational acceleration. A body weighs less on top of the mountain since local gravitational acceleration decreases with altitude. Interesting. It should be g of z, or it's a function of space and time. On the surface of the moon, an astronaut weighs about 1/6 of what he or she normally weighs on Earth. That's pretty interesting. So my fat ass, not so fat on the moon. I take it back. At sea level, a mass of 1 kilogram, 9.807 newtons, is illustrated in Figure 110. That's this. A mass of 1 pound mass, however, weighs 1 pound force, which misleads people into believing that pound mass and pound force can be used interchangeably as lbs, which is a major source of error in the English system. Like, that seems pretty important. So lbs do not equal lbms. One lbf is 32 lbm. 1 gravity is 32.17 feet per second squared. Cock. It should be noted that gravity force acting on the mass is due to the attraction between the masses, and thus is proportional to the magnitudes of the masses and inversely proportional to the square of the distance between them. Therefore, gravitational acceleration at a location depends on latitude, the distance to the center of the Earth, and to a lesser extent, the position of the Moon and the Sun. The value of g varies with location from 9.832 meters per second squared at the poles, 9.789 at the equator, to 7.322 meters per second squared at 1,000 kilometers above sea level. At altitudes above or up to 30 kilometers, the variation of G from sea level value of 9.08 is less than 1%. Altitudes above 30 kilometers, the variation from sea level is less than 1%. Oh, but 1,000 kilometers? That is more than 1%. For most practical purposes, the gravitational acceleration can be assumed to be constant at 9.81 meters per second squared. Interesting to note, at locations below sea level, the value of G increases with distance from sea level, reaches a maximum at about 4,500 meters, then starts decreasing. What do you think the value of G is at the center of the Earth? Well, it's proportional to the distance of two bodies squared, so or the root of the distance between the two bodies squared, like you just said. Inversely proportional to the square of the distance between them. So, inversely proportional. Let's figure it out. So we got 1 over x equal to G. Like M1, M2. The magnitude of the masses. So, as this approaches lim, as x approaches 0, G approaches infinity. 1 over a really small number is infinity. And infinity times anything is infinity, so yeah. That doesn't make sense. Somehow this mass, like these two somehow the relationship between these two masses becomes the same. Or like, it's probably like M1 plus M2 times the who knows. The primary cause of confusion between mass and weight is that mass is measured indirectly by measuring the gravity force it exerts. This approach also assumes that the forces exerted by other effects, such as buoyancy and fluid motion, are negligible. This is like measuring the distance to a star by measuring its redshift, or measuring the altitude of an airplane by measuring barometric pressure. Both these are indirect measurements. The correct direct way of measuring mass is to compare it to a known mass. However, this is cumbersome, and it is mostly used for calibration and measuring precious metals. Work, which is a form of energy, can be simply defined as force times distance. Therefore, it has the unit Newton meter, which is called a joule. That is, 1 joule is equal to 1 Newton meter. We got formula 1.3. A more common unit for energy is the kilojoule. In the English unit system is a BTU, British thermal unit. which is defined as the energy required to raise the temperature of 1 pound mass of water at 68 degrees Fahrenheit by 1 degree Fahrenheit. In the metric system, the amount of energy needed to raise temperature of 1 gram of water at 14.5 degrees Celsius is defined as 1 calorie. And 1 calorie is 4.187 joules. If you light a typical match and let it burn itself out, it yields approximately 1 BTU, or 1 kilojoule of energy. Interesting. The unit of time rate of energy per joule per second, which is called a watt. Watt! In the case of work, time rate of energy is called power. A commonly used unit of power is horsepower, which is equivalent to 746 watts. Electrical energy typically is expressed in the unit of kilowatt hour, which is equivalent to 3,600 kilojoules. An electric appliance with a rated power of 1 kilowatt consumes 1 kilowatt hour of electricity when running continuously for 1 hour, which would be 3,600 kilojoules. Right? Yeah. Which is 3,600 newton meters per second. Yeah. No. A joule is a newton meter. Yeah. And a watt is, yeah. Oof. When dealing with electric power generation, the units of kilowatt and kilowatt hour are often confused. Note that kilowatt or kilojoule per second is a unit of power, whereas kilowatt hour is a unit of energy. Therefore, statements like the new wind turbine will generate 50 kilowatts of electricity per year are meaningless and incorrect. A correct statement should be something like the new wind power with a rated power of 50 kilowatt will generate 120,000 kilowatt hour of electricity per year. Dimensional homogeneity. Basically, we got an example problem. Example 1-1. Okay, great. So we got, you see that? Oh yeah. The school's paying 12 cents per kilowatt hour of electricity. If a wind turbine that's rated for 30 kilowatts that averages operating for 2,200 hours per year, how much electricity, how many dollars can be saved? $7,920 of electricity saved per year, which is 6,600 kilowatt hours per year, produced from the wind turbine. Okay, great. We all know from this experience, units give terrible headaches if they are not used carefully in solving a problem. However, with some attention and skill, units can be used to our advantage. They can be used to check formulas. Sometimes they can even be used to derive formulas, as explained in the following example. Alright, they fill a tank with oil. Here's the picture. Big a big picture. A big picture. Anyhow, we got a 2 meter cube tank. The density that it's filled, the oil that is 850 kilograms per meter cubed. What's the mass? Mass is equal to, well, density is equal to mass over volume. Rho equal m over v. So m equal rho times v. Rho equal m over v. M equal rho times v. 850 times 2 is 1700 kilograms. Alright. Keep her moving. Unit conversion ratios. Oh yeah, keep in mind that a formula is not dimensionally homogeneous is definitely wrong, but a dimensionally homogeneous formula is not necessarily right. Basically, this reminds me of when we were doing regression analyses for sizing an absorption or a cooling tower. The formulas we had there were correct, but they were not dimensionally homogeneous. And that was a learning experience for me. So, keep her moving. Just as non-primary dimensions can be formed by suitable combinations of primary dimensions, all 9 non-primary secondary units can be formed in combinations of primary units. Force units, for example, can be expressed 1 Newton is equal to 1 kilogram meter per second squared, and 1 pound force equal to 32.174 pound mass feet per second squared. They can also be more conveniently as unit conversion ratios. Bada bing, bada boom. Unit conversion ratios are identically equal to 1 and are unitless, and thus such ratios, or their inverses, can be inserted conveniently into any calculation to properly convert units. You are encouraged to always use unity conversion ratios, such as those given here, when converting units. Some textbooks insert archaic gravitational constant defined as GC is equal to 32.174 pound mass per pound force times second squared is equal to 1 kilogram meter per Newton second squared is equal to 1 into equations in order to force units to match. This practice leads to unnecessary confusion and is strongly discouraged by the present authors. We recommend that you instead use unity conversion ratios. Interesting. The weight of 1 kilogram. Basically, weight is equal to mass times gravity. You're given 1 kilogram. How many newtons? Figure out how many newtons. Okay? Okay, great. So, 1 kilogram times gravity, 9.807 meters per second squared at sea level, localized on Earth. With a unity unit conversion, 1 Newton per 1 kilogram meters per second squared is equal to 9.807 newtons. The quantity in the large parentheses in the equation is the unity conversion ratio. Mass is the same regardless of location. Like, this should be tabbed. The unity, every unity conversion ratio, as well as its inverse. I don't have the tabs on me, but we'll dog-ear it. I'll be right back. 20 minutes in, times 2. Stay hydrated, my friends. Alright. We're all keep her moving. When you buy a box of breakfast cereal, net weight 1 pound, technically this means that the cereal inside the box weighs 1 pound force on Earth and has a mass of 453.6 grams at sea level. 1 pound on Earth at sea level. Therefore, it weighs 4.49 newtons. The actual weight. Not the... Yeah. Oh, check this out. I thought a gram was a unit of mass. Newton Crunch cereal. What does that say? The breakfast of engineers. Oh. This is a good book. A system defined. Alright, keep her moving. Systems and control volumes. A system is defined as a quantity of matter or region in space chosen for study. The mass of the region outside of the system is called the surroundings. The real or imaginary surface that separates the boundary system from its surroundings is called the boundary. The boundary of a system can be fixed or movable. Note, the boundary is the contact surface shared by both the system and the surroundings. Mathematically speaking, the boundary has zero thickness, and thus it can neither contain any mass nor occupy any volume or space. This is very abstract. Systems may be considered closed or open, depending on whether a fixed mass or fixed volume in space is chosen for the study. A closed system, also known as a control mass or just system, when the context makes it clear, consists of a fixed amount of mass, and no mass can cross its boundary. That is, no mass can enter or leave a closed system, as shown in Figure 1.19, but energy in the form of heat or work can cross the boundary. The volume of a closed system does not have to be fixed. If, as a special case, even energy is not allowed to cross the boundary, that system is called an isolated system. There's a Muse song that talks of isolated system. I am the de facto free. Yes, I am free from your intersociety. Consider the piston cylinder device shown in Figure 1-20. Let us say 1-20. Alright. A closed system with a moving boundary. Let us say, who doesn't like a good piston action? Let us say that we would like to find out what happens to the enclosed gas when it is heated. Since we are focusing our attention on the gas, it is our system, the inner surfaces of the piston and the cylinder from the boundary. And since no mass is crossing this boundary, it is a closed system. Notice that energy may cross the boundary, and part of the boundary, the inner surface of the piston, in this case, may move. Everything outside of the gas, including the piston and the cylinder, is the surroundings. An open system, or a control volume, as it is often called, is a properly selected region in space. It usually encloses a device that involves mass flow, such as a compressor, turbine, or nozzle. Flow through these devices is best studied by selecting the region within the device has a control volume. Both mass and energy can cross the boundary of a control volume. A large number of engineering problems involve mass flow in and out of a system, and therefore are modeled as control volumes. A water heater, a car radiator, a turbine, and a compressor all involve mass flow and should be analyzed as control volumes, open systems, instead of control masses, closed systems. In general, an arbitrary region in space can be selected as a control volume. There are no concrete rules for the selection of control volumes, but the proper choice certainly makes the analysis much easier. If we were to analyze the flow through an air nozzle, for example, a good choice for the control volume would be the region within the nozzle. As we can see here, imaginary boundary, real boundary. Control volume with a real and imaginary boundary. This is the control volume of a nozzle. The boundary of a control volume is called a control surface, and they can be real or imaginary. In the case of a nozzle, the inner surface of the nozzle forms a real part of the boundary, and the entrance and exit form the imaginary part. The little dotted lines, imaginary, real. This figure is a little misleading with the imaginary boundary because the dotted line is not overlapping the thick line, but they describe it that way. A control volume can be fixed in size and shape, and in the case of the nozzle, or it may involve a moving boundary as shown in figure 121b. Most control volumes, however, have fixed boundaries and thus do not involve any moving boundaries. A control volume can also involve heat and work interactions, just as a closed system, in addition to mass interaction. We're learning together, one step at a time, one page at a time. Alright, keep her moving. As an example of an open system, consider the water heater shown in figure 122. Let us say that we would like to determine how much heat we must transfer to the water in the tank in order to supply a steady stream of hot water. Since hot water will leave the tank and be replaced by cold water, it is not convenient to choose a fixed mass as our system for the analysis. Instead, we concentrate our attention on the volume formed by the interior surfaces of the tank and consider the hot or cold water streams as mass leaving and entering the control volume. The interior surfaces of the tank form the control surface for this case, and mass is crossing the control surface at two locations. In an engineering analysis, the system under study must be defined carefully. In most cases, the system investigated is quite simple and obvious, and defining the system may seem like a tedious and unnecessary task. In other cases, however, the system under study may be rather involved, and a proper choice of the system may greatly simplify the analysis. Yeah. Agreed. Properties of a system. 1.4. Any characteristic of a system is called a property. Some familiar properties are pressure, temperature, volume, and mass. The list can be extended to include less familiar ones such as viscosity, thermal conductivity, modulus of elasticity, thermal expansion coefficient, electric resistivity, and even velocity and elevation.